Good morning everyone. Myself Devangshi Kalita, and I have done my MSc in Physics from Pondicherry University and BSc from Guwahati University. And I have qualified this exam, CSR NET, GATE, IIT JAM, ZEST, BARC Scientific Officer exam. This exam I already qualified. And currently I joined as a PhD student in IIT Guwahati. So in this video I will teach about solid state physics, and basically this course will be for CSR NET exam and GATE exam purpose. So let's start the outline of this course. So first I will teach you about crystallography. I made some subdivision of this topic, crystallography, A, B, C, D I mentioned like this. So at first I will teach you about concept of space and Bravais lattice, and then I will teach you X-ray diffraction, and then reciprocal lattice, and then some previous year question. So it needs almost 10 hours to finish all this topic, crystallography topic. And next, after completing this crystallography, then I will move to density of state. Here also I mentioned some subtopic of this topic. So first I will teach you 1D, 2D, 3D cases for non-relativistic free electrons, then relativistic free electrons, then photons, then phonons, then magnons, and then some previous year question. This also needs almost 10 hours to complete all these density of state topics. Then after that I will move to lattice vibration. So first I will teach you lattice vibration in 1D monatomic crystal, then I will teach you lattice vibration of 1D diatomic crystal. For diatomic case we need two different process to study this diatomic case. So here first is acoustic branch and second is optical branch, and then I will teach you some previous year question. I will discuss some previous year question of IIT JAM, ZEST, CSR NET and GATE. For this type of question I will discuss here. Then this also need almost 10 hours to finish this lattice vibration topic. So that after that I will teach you specific heat of solids. So here is at first I will teach you concept of internal energy and temperature, then I will teach you classical theory of specific heat. Then in the classical theory of specific heat there is a law, Dulong-Petit law, which I will teach you after that. And then quantum theory, I will move to the quantum theory of specific heat. And then this also need total 10 hours to finish this specific heat of solid course. And then after that I will teach you free electron theory. Here also at first I will teach you specific heat of metals, then Rood models, then Hall effect, and at the end some previous year questions. Then after completing this I will move to the band theory of solids, and this actually a little broad topic is so it needs little more time, and I here mention almost 20 hours I need to complete this whole topics. So at first I will teach you classification of solids, then block functions, then Crony-Penny model. After that I will teach you brilliant zone concept, then group velocity and effective mass concept, and then at the end I will teach you tight binding approximation model. So this is the outline of our solid state physics course. So now I'm going to teach you classical theory of specific heat. Classical theory of specific heat. Theory of specific heat. I'm going to teach you this. So as I already told you that there is two theory to study the specific heat. One is classical, one is quantum. So now in this lecture I will tell you about the classical theory. So what is the classical theory? According to this theory, atom in solid behave as classical oscillator. Atom in solid behave as classical oscillator. Classical oscillator. If we draw the diagram, what will be the diagram for this? Let's suppose this is the atom. This is the atom. In real, it is three-dimensional case, but for understanding, I draw this in two-dimensional. And let's introduce some spring among the atoms. Actually, the spring is not present in real case. For understanding, I have drawn this spring so that this oscillation motion can understand better way. So this atom actually oscillate among the mean position. So this is a two-dimensional case, but in the three-dimensional case, this oscillation in three different directions. This oscillation can happen in x direction, in y direction, and in z direction. X, Y, Z. So three different directions can be possible for oscillation for these atoms. So I hope you understand this concept, oscillation concept. And now for understanding this classical theory, you have to know other terms is about this equipartition of energy. What is the equipartition of energy? The average energy per degree of freedom. Energy per degree of freedom is half kT. This is the equipartition of energy. This concept will be useful after some times for this derivation. So what is the now CV? What is the value of CV? CV means specific heat. CV equal to du by dt. I hope you already know about this du by dt value. So what is the, to calculate this, we have to know first U value. What is the internal energy for this system? So what is the internal energy? U equal to total transverse kinetic energy, rotational kinetic energy, plus vibrational kinetic energy, plus vibrational potential energy. This is the sum of this four energy, total internal energy for one atom. This U is for only one atom. So what in this case, transverse kinetic energy will be zero, because atom are oscillating, not they are only oscillating atomers. So they are not in the transverse motion. So this will be zero. And rotational kinetic energy also will be zero, because there is no rotation in this case. Only these two will be survived. So what will be this value? This value will be half m x dot square plus half m y dot square plus half m z dot square plus half beta x square plus half beta y square plus half beta z square. This will be survive only. And according to the equipartition of energy, this value will be, all 6 times value will be half kT, half kT, half kT. So total sum will be 6 by 2 kT. And this will be thrice kT. I hope you understand. This only for one atom. Only one atom. And what about for n number of atoms? For n atom, for n number of atoms, this will be thrice n kT. And for 1 mole of atom, what will be happen? For 1 mole of atom, n will be Na. So this derivation will be thrice Na kT. So then what is the specific heat? Cv equal to du by dt. Put this value here, and this will be thrice Nak. And what about Nak? Na equal to K equal to thrice R. So this is the actually expression for specific heat in classical theory. So what is this value? This value will be almost 25 joule per Kelvin. This is the expression.